Welcome back to your lab tutorial. I think we should take some time and talk about time constants. In this lab, you are going to measure the time constant with various combinations of capacitors. You're going to make nice, pretty little graphs. You'll find out that your graph is pretty well spot on, an amazing curve fit. Should make you pretty happy. And then you're going to calculate the capacitance of various arrangements of capacitors. So the theory, I like to think of capacitors as kind of the junk closet of charge. You hook it up to a battery, a little bit of charge flows over here. So then you start getting these charges that are piling up. Alright, so charges pile up on this side. And what happens? The more you pile up, the harder this pushes back. Alright, so you get this induced electric field going this way, which opposes E, set up by the battery. This one right here. So the battery is pushing this way in the direction of E, and then all the charge you pile up pushes the other way until this capacitor reaches its maximum charge. And if you think about it, as this charge gets piled up, it gets harder and harder to put more charge over. So you'll start charging really, really fast. You'll start charging up from 0, you'll go, whoa, and then you'll start slowing down. Not unlike this closet. Now, at first you'll just put a vacuum cleaner, maybe a couple coats, but then, well, everything starts going in. It gets harder and harder to put more charge over there. But what we're interested in is this discharge curve. So we'll flip the switch, which is great. It feels like a nice little Frankenstein switch. Have mad scientist moment if you'd like. When you flip the switch, you'll connect it to this resistor, and then the charge that's stored on this plate pushes off each other and flows through this resistor. But as it goes through, you'll notice you get a whole bunch of charge at the very beginning, so it flies off real fast, so a huge drop, and then it kind of planes out. And we'll talk about this in class, about the theory and what type of shape you should get and what it looks like. But I want to leave some of the mystery alive for lab. That way you can see it and be like, I think I see the mystery. Now, in order to actually see this, one of the things we should do is calibrate this. So you'll go to the differential voltage probe experiment in Logger Pro, go to the experiment tab, calibrate, and select channel 1 differential voltage probes. There's only one option, so it should be pretty easy to find. Then you'll hit calibrate now, because as mentioned, we want to calibrate this system. And then you will take the two leads and clip them together. They're like a little fishing bobber, so just kind of make them hold hands, and this would be your 0 volts. And then you'll hit keep, and then you'll plug into this side, and oh, the ground's over here, or sorry, yeah, the ground, GR, and D is over on this side. You'll connect to these two probes, and you'll measure it with this handy dandy meter, and let's say this reads at 6.2 volts. It could be anything. You're going to read it with the actual reader, and then you would plug in 6.2 into this number, 0 into there, and then your system's calibrated. Now, as your lab handout talked about, you get this V equals V naught e to the minus t. This is your actual time over RC. And if you think about this, this is because you're pushing that charge through. Resistance is going to slow down that flow of charge. Capacitance is how big the capacitor is, how big your initial push is. And this is E, this is your exponential function, because push really hard at the beginning, not as much as the charge bleeds off. All you're doing with these values, this 6.2, that's just your V naught. It just affects the constant. The shape of your curve is given by this exponential feature right here. So it doesn't really matter, it just gives you a more accurate number for your initial value, not necessarily the curve fit. Now we're ready to look at the capacitors. So capacitors, this thing right here, looks kind of like a virus. Couple keynotes. The value it should be is on the side. So this is 47 microfarads. And this silver line indicates the negative. These are electrolytic capacitors, so make sure, silver line, make sure that this goes to the ground. Alright? And the reason is, when it's an electrolyte, there's this chemical reaction that takes place. It builds up a metal oxide layer that charges up in one direction. If you put it backwards, you strip the metal oxide layer. It sounds like popcorn, it smokes, and it smells really bad. Oh, and it stops working, so please don't do that. So always make sure that your silver line goes to ground. Alright. Now we've got your circuit set up. So the capacitor, oh, notice silver side to ground. This right here is that Frankenstein switch that I mentioned. something you've all been dying to do. So right now, if we follow this, this is discharging the capacitor. You can tell because it's using the capacitor, the resistor, and goes through here. If you want to charge the capacitor, flip it over to this side, and then it goes from the battery through here, back to the ground. All right. So charging is this way, discharging is this way. You'll charge it up. You will watch your little graph as the voltage steadily goes up. It'll go doot, 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 until it kind of levels off, and then you will flip the switch. Now, as we've talked about this, since you actually want to measure the voltage across the capacitor, please make sure that you connect the red lead right here and the black lead to the other side on the ground. Otherwise it just flips, you get a negative sign. Not a big deal, but you know, why do that? Yeah. So this is how you measure the voltage. Again, they're like little bobbers. Push the back, little hook comes out and you can clip it to whatever you need. This is your resistor. Measure this with the multimeter. Don't trust any actual values, always measure them. And then for your data collection, you're going to graph the discharge curve. All right, get your discharge curve. Then you will do a fit, and we have this V equals V naught e to the minus t over RC. So the fit you are going to do is called natural exponent. It should look like a curve, and this should be under the curve fit menu. And then you will record C from the graph, which is actually 1 over RC, unfortunately, where C is the capacitance you actually want, and then your plus or minus uncertainty. This is how you get your error in this lab. It is pretty easy because the graph tells you. All right. For your error analysis, as we've mentioned, you get the plus minus for C in the graph. You can't make this error translate directly to your capacitance just as a number, so we need to convert this to a percent. And then you'll also get a percent from your resistor reading. Again, check the manual for your multimeter and it'll be in there. All right. So the wrap up, what are you trying to do? You're going to calibrate your sensor. Then you're going to run each capacitor individually and get the actual capacitance for each capacitor. The reason you're getting the actual values, don't trust what's written on the side. They could be 10-20% off. Not so great. Then you're going to go through the later parts of the experiment where you will use the actual capacitances from experiment 1, along with the parallel and series formulas to calculate the theoretical value, and you'll get your experimental value from C graph. So by the end, you'll have some very nice voltage plots. You only need to print one though, but the others are, very nice. It's satisfying to have a curve fit that actually looks like what it's supposed to. A whole bunch of C graphs, a bunch of capacitor values, and always, always, always make sure that the silver points to the ground. I will see you in lab.